Hello, this is Math Jess from Almost Cool. This is my third live stream, and so if any of you have any calculus questions, please email them to the address on the screen, and I will get to them as they come. Until we start getting questions on the live stream, I will be answering questions from a set of questions I prepared for this exam. So, without any further ado, we will start working on a question. So, there we go. Our first question is to prove, using implicit differentiation, the derivative of arctangent. So, find and prove the derivative of arctangent. So, the first thing that we're going to do is we're going to write out a function y equals arctangent of x. And then we will solve for x. So we get tangent of y is equal to x. From here, we're going to use implicit differentiation to take the derivative of both sides of this equation. And we get secant squared of y is equal to 1. Or sorry, secant squared y prime is equal to 1. We will solve for y, or y prime, getting y prime equals cosine squared of y. Now from here, we're going to have to draw a triangle and figure out what the cosine of y would be. So let us draw such a triangle. Here's our triangle. So if this angle here next to the point 2, 0 is the angle that we're going to call y, that means that the opposite side of the triangle is the one that lies on the y-axis. The adjacent side is the side that lies on the x-axis, and the hypotenuse is, of course, the line that we drew connecting the point 0, 1 and the point 2, 0. So we know that from our assumption that tangent of y equals x, we know that the opposite side divided by the adjacent side is going to be x. So if the opposite side is x and the adjacent side is 1, that gives us the ratio we choose to have. So let us write that down. Opposite equals x. The adjacent equals 1. And by the Pythagorean theorem, we get that the hypotenuse is equal to the square root of x squared plus 1. So we now go back to this equation for y prime. And we say, well, y prime equals the cosine squared of y. The cosine is going to be the adjacent side divided by the hypotenuse. The adjacent side is 1, and the hypotenuse is the square root of x squared plus 1. So the resulting equation we get is going to be y prime equals 1 divided by the square root of x squared plus 1, but we're going to square this fraction. So we're just going to end up with 1 divided by x squared plus 1. And the traditional form of this is going to be y prime equals 1 over x squared plus 1. And this is our beautiful traditional form fraction. Thank you, Alex. So there are no questions on the docket yet, so we will go to another question I prepared. And if you want to see this question for a longer amount of time, you can either rewind to the live stream, or you can, if this is after the video is posted to YouTube, you can just pause and examine it. Next question. We have, let's find the maximum and minimum values of x cubed minus 2x squared plus 4x plus 2 on the interval 0 to 3. So for this problem, we're going to have to take the derivative and find out where the derivative equals 0. Since this is a polynomial, we know it has a derivative everywhere, so we don't need to worry about finding places where the derivative doesn't exist. But we'll find all of the places where the derivative equals 0, and then we'll check the ones of those values that are in the interval against each other and the endpoints. And the largest of these values is going to be the maximum, and the smallest of these values will be the minimum. So the derivative is going to be, the derivative is going to be 3x squared minus 4x plus 4. So we can use the quadratic formula, or we can try and factor this, or whatever way we want to get the roots. We won't worry too much about. We'll just make Mathematica give us the roots. But, oh my, I lost it. Anyway, we had, oh, there we are. I found it again. Okay, so we will have Mathematica solve this equation for us to figure out where this expression equals 0. We have 3x squared minus 4x plus 4 is 0. We get that this function here, all of its roots are imaginary, as given by these i's here. So that means that we have no places where the derivative equals 0, or at least no places on the real number line. We're only doing calculus on the real number line for this video. So that means that that the maximum and minimum values are going to occur at the endpoints of this interval. So we plug in 0, and we get out 4. So if this was our function f, then we have f of 0 equals 4. And if we plug in 3, we get f of 3 equals 3 times 3 squared, which is 27, minus 4 times 3, which is 12, plus 4, which is going to be 19. And that tells us that 3 is the maximizer of f on the interval, and that the maximum value is 19. We also know that 0 is the minimizer of f on the interval. The minimum value is going to be 4. So this was kind of a trivial example because we found that there were no local maxima or minima on the interval given. Okay, let's do this again, or this problem again, but we're going to change the polynomial we use. So instead of using x cubed minus 2x squared plus 4x minus 2, we're just going to flip this sign to be a negative 4x. So we're going to get the same process to figure out where the maximum and minimum values are, but this time the derivative will have a negative sign there. When we solve, we'll have a negative sign here. We get negative 2/3 and 2 as our critical values. Negative 2/3 is outside the interval, so we ignore it. But now we need to calculate f of 0, f of 3, and f of 2. So if we plug 0 into the derivative, we get negative 4. If we plug 2 into the derivative, we get 3 times 2 squared. 2 squared is 4, and 3 times 4 is 12. Minus 4 times 2, so that's minus 8, minus 4. And that's right. I plugged 2 into the derivative. I should have plugged 2 into the function, the original function. And it seems like I made that mistake on the last problem. We will come back to the last problem and do it correctly. I am sorry. So f of 2 will be 2 to the third is 8, minus 2 times 2 squared, which is negative 8, minus 4 times 2, which is going to be negative 8, plus 2. And we're going to end up with negative 6. F of 3 is going to be 3 cubed, which is 27, minus, 3 cubed is 27, minus 2 times 2 squared, so that's going to be negative 18. We have negative 4 times 3 is negative 12, plus 2. And that is going to equal, we have 9 minus 12 is negative 3, plus 2 is negative 1. And if I plug 0 into the original function, I get 2. Those are the correct values of the correct functions. I'm sorry for the error, but we fixed it. And we'll come back to the other problem. Okay, so now that we have these values, we see that negative 6 is the smallest value, and 2 is the largest value. So that means that 2 is the maximum value of f on the interval, with 0 being the maximizer, and 2 is the minimum value. Sorry, -6 is the minimum value, with 2 being the minimizer. Okay, so we'll go back and fix this. We'll put this back as positive 4. This is the original problem again. That makes this a positive 4, this a positive 4. We still end up with no roots in the interval. No real roots at all, actually. And then we plug in 0 into f. This equation, I'm sorry, I grabbed the derivative. I should have plugged 0 into the original equation, the original function. F of 0 will be 2. F of 3 is going to be 27 minus 18 plus 12 plus 2. And we end up with looks like, well, 27 minus 18 is 9, plus 12 is 21, plus 2 is 23. So for this problem, we have 2 is the minimum value of f on the interval, with 0 being the minimizer. And 23 is the maximum value, with 3 being the maximizer. Okay. The next problem will be find the tangent line for the equation x cosine of y equals y cosine of x There may be more than one tangent line, so we'll put tangent lines at x equals 0. Okay, so the first thing that we need to do is, the first thing I'm going to do is I'm going to find out what points are on the graph of this equation with x coordinates of 0. So we plug in x is 0, we get 0 times cosine y, so we get 0 is equal to cosine of, sorry, y times cosine of 0. So that's 0 equals y. The 0 here kills the left side of the equation. The 0 here gets fed into cosine. Cosine of 0 is 1. So we get 0 equals y. And that's the only point that works. So that means we want the tangent line at the point x is 0, y is 0. So the first thing that we're going to do is we're going to use the second thing we're going to do is we're going to use implicit differentiation to take the derivative of this equation. We notice each side is a product rule, so we will use the product rule on both sides. We have the derivative of the first equation, which is x. Derivative of x is 1. So I have 1 times cosine y plus x times the derivative of cosine y is negative sine. And then since the inside function was y, the chain rule says we have to multiply by the derivative of that, so we get y prime. On the other side of the equation, we do the same thing. We have a product rule. So the derivative of the first function is y prime times cosine of x. And then we will add y times the derivative of cosine, which is negative sine x. And that flips the sign here. Put a traditional form around it. There we go. Beautiful equation right here. Okay, so the next thing that we need to do is we need to solve for y prime. So we're going to take everything that has a y prime and stick it on one side of the equation, and everything that does not have a y prime and put it on the other side of the equation. So we get cosine of x plus sine of y, or x sine of y, times y prime. I factored the y prime out of these two terms, this one and this one, after moving them onto the same side of the equation. And that will equal cosine of y plus y sine of x. So notice that this function and this function ended up on the same side because there are no y primes in them. This term and that term are on the same side because they have no y primes. And this term and this term ended up on the same side. The opposite side is the other two because they have y primes in them. I factored out the y prime, so I get this. And now I divide both sides by the coefficient on y prime so that I can isolate y prime. Like so. This goes to the other side. And now I'm going to plug in the point x is 0, y is 0. Because that's the only point on the curve that has an x coordinate of 0. So this is a 0, and this is a 0. I'm just plugging in all of the zeros. And I end up with y prime equals 1. So this means that the tangent line for this curve has a slope of 1. We also know that this curve passes through the point 0, 0. So in slope-intercept form, or in point-slope form, let's do that one, we get y minus y naught so the y-coordinate, equals the slope times x minus the x-coordinate. So y equals x is the function that has that goes through the point 0, 0 and has a slope of 1. And for interest's sake, let's plot this. So we will do, let's see. We should plot this. Let me figure out how to plot this. So I think it's a density plot. Here we go. Let's see if this works. It's definitely some kind of plot, though. Let's try contour plot. And capitalize that. Bracket, bracket, capitalize, bracket, bracket. There we go. Oh, that's kind of a cool looking graph. Here, let's extend the range of the graph a little bit. Oh, that is very pretty. That was worth the wait. Oh, isn't that gorgeous? Check it out. That's beautiful. Oh, hi, Mark. You have any calculus questions? I see you, Mark. Okay, so let's go on to another problem. Okay, so we'll kill all of this output. That was a pretty graph, though. The next problem. Find the 99th derivative of sine of x plus e to the x plus x to the 7th. Okay, so we do know that the derivative of a sum is the sum of derivatives. That is, if we have a function f plus a function g, and we take the derivative, it's the same as having the derivative of f plus the derivative of g. And so it's not so hard to see why the 99th derivative of a function works the same way. So we're going to split up these three functions that are being added together and take the 99th derivative of each of them one at a time. Okay? So let's start with x to the 7th. So x to the 7th, you might already see what's going to happen here, but x to the 7th's derivative will be 7x to the 6th, and that thing's derivative is going to be 7 times 6x to the 5th, and we'll get 7 times 6 times 5x raised to the 4th, until eventually we get to this point where we'll have 7 factorial times x raised to the 0 power. And when we take the derivative of that, we're going to get 0 times 7 factorial times x to the negative 1. But 0 times anything is 0. So eventually, we're just going to get a chain of zeros for our derivatives. It's might be sad, but it's definitely true. At what point does that happen? Well, it's going to happen. It takes 7 derivatives to get to this point. So this is the 8th derivative. 8th derivative is 0, and we definitely hit 8 before we hit 99. So this part at the end, this x to the 7th, its contribution to the derivative is 0. So now we look at e to the x. Well, e to the x is its own derivative. So every time we take the derivative, we just end up with e to the x again. So the 99th derivative of e to the x is still e to the x. So let's write these down. X to the 7th goes to 0. And e to the x goes to e to the x. And then we need the 99th derivative of sine. Well, the derivative of sine is cosine. Which goes to negative sine, which goes to negative cosine, which goes back to sine. So what that means is that the 4th derivative, here's our function, 1, 2, 3, 4th derivative is the original function. That means the 8th derivative will also be the original function, as will the 12th and the 16th, and basically every number that's divisible by 4, that derivative will be sine of x. So we have to figure out, what is 99 divided by 4? Well, 99 over 4 is going to be, it's going to be 24 3/4. Or, in other words, we will cycle 24 times between all of our derivatives and then go 3 steps further. So this will be the 96th derivative because it's the one that's divisible by 4. This is after we've cycled 24 times through, we'll land on this one. And then this will be the 97th, the 98th, the 99th, negative cosine of x. If we took one more derivative, we'd get to 100, which would be 25 complete cycles ending on sine. So our answer is going to be that sine of x goes to negative cosine of x. And then we just add these three derivatives together. So negative cosine of x plus e to the x plus 0. We'll wrap it up nicely in a traditional form box, is our 99th derivative. Guess we could do, let's see, d 99 over dx to the 99. Let's see if this wraps. Not exactly what I wanted, but it actually is a correct. This notation is correct even if it's not pretty. Okay, so let's try doing another problem. Check the email. We have no current problems on the email. So let's do another one. So we are going to take the derivative of the natural log of the square root of x divided by x plus 1. So this is the function that we're going to take the derivative of. We could use the chain rule and the quotient rule, but I think that the easiest way to take care of this is by using the properties of the log function. Remember, in Mathematica, log, log, with no base represented, or no base written, is log base e, or the natural log, that is ln. For most textbooks, especially most first-year college textbooks, log with no base written refers to the common log, which is log base 10. But on Mathematica, log base e is written log. And I'm going to stick with that convention. So we're going to say that the natural log of, well, first we can take a power down. That's 1/2 power. We get a log of x over x plus 1. We can simplify further because division inside of a log becomes subtraction on the outside of a log. And the coefficient distributes. From here, we can now take the derivative. So the derivative of log of x is 1 over x. Multiply that by 1/2, we get 1 over 2x. The derivative of log of x plus 1 is going to be the derivative of what's inside the log function, so 1. The derivative of x plus 1 is 1, divided by the original function, which is x plus 1. But we have a coefficient of 2, so we're going to have to multiply the denominator by 2. Or that's a coefficient of 1 over 2, coefficient of 1/2. And let's put these in traditional form boxes. and it looks beautiful. This is our derivative. 1 over 2x minus 1 over 2 times x plus 1. Okay, so let's do another problem. Let's find, okay, so we're going to suppose that, okay, this will be whimsical, but it'll be fun. We're going to suppose, let's convert this to a text cell. We're going to suppose that we have a world where all bubbles are cubes. Suppose that bubbles are cubes. So that means that if we're blowing up a bubble, the volume of the bubble is going to increase by the rate at which we pump air into it. So let's say if the volume of a cube bubble is increasing at, let's say, like 24 cubic inches a second. Okay, we'll just call that 24. At what rate are the sides of the cube expanding or increasing? When the volume is maybe, let's pick a cube, let's pick 8. 8 cubic inches. There we go. The units don't particularly matter because we pick the same volume and length units the whole way through. We could pick meters or centimeters or inches or feet or yards or anything. If we had 2 different units, then we might have to convert, say we had like centimeters and inches. Then we'd want to change one into the other. But since the units are all the same, they don't particularly matter. Anyway, so let's write down the formula for the volume of a cube. So volume is equal to the length of a side cubed. Almost makes you wonder if there's a relationship between cubes being third powers and cubes the geometric figure, right? Anyway, so we want to have 2 equal signs there so that we, yes, thank you, Mathematica. Okay, so we have this equation here. There we go. We have this equation here, volume equals s cubed. So we are going to take a derivative of both sides. That'll give us v prime is equal to 3s cubed, or sorry, s squared times s prime. So we know that v prime is going to be 24, and we know that our volume is 8. Okay, so we don't know what s is right now, but we'll write that into the equation. We don't know what s is right now, but we do know that there's a relationship between the volume and the side length. And we do know that our volume is 8 at the time that we're interested in. So 8 equals s cubed, taking the cube root, gives us 2 equals s. So we can plug that in to this equation. We get 3 times 2 squared times s prime. Well, 2 squared is 4, times 3 is 12, s prime. But we divide both sides by 12, and we're going to get 2 equals s prime. That tells us that at the instant that we're concerned with, the derivative of the length of the side is 2. Or that means that we're increasing it 2 inches per, I think we said, second. That's a very rapidly increasing bubble. Okay. That was a fun problem. Cubical bubbles. I guess we could do conical bubbles, and that'd be just as bizarre. We might save conical bubbles for another time. Or maybe just later in the... Oh, we're almost out of time. I think we have time to do one more problem, and then we'll stop. Let's see. What problem do I want to do? Oh, here's one. So let's say that we want to evaluate the limit is there a hey the limit as I don't know the limit command off the top of my head, but we'll take the limit as theta goes to 0 of this fraction. So we'll go sine of 3x times sine of 6x divided by, let's see, 4x squared. Oh, wait. I have to put parentheses around the denominator, or else it won't recognize this properly. So we want to compute the limit of this as x goes to 0. Now, one thing that we do know is we do know that the limit of sine of x over x as x goes to 0 is 1. So we notice that we have 2 sines in the numerator and an x squared in the denominator. So if we can just split this into a sine over x and a sine over x, we'd be getting somewhere closer to something that we've already memorized. So I'm going to do this. I'm going to split this fraction into 2 fractions being multiplied by each other. I'm going to take the 1/4 completely out of the limit. It's a constant, so we'll just take this 1/4 out in front. We need to close our parenthesis. There we go. So, oh, it doesn't like to split this up. Well, there we go. Now we've split it up. The thing is that 3x gets to 0 at a different rate than x does. We can fix this by multiplying by 3 over 3 and multiplying by 6 over 6. Doing that, we get this. Oh, I need to put parentheses here. There we go. Notice how we had just x's by themselves in the denominators of these 2 fractions, this one and this one. But to get the denominator to match the argument of sine, we had to divide by 3. And to get the argument here to match up the sign, we had to divide by 6. And so the way to fix that is by multiplying the whole thing by 3 and 6 on the top and dividing by 3 and 6 on the bottom. It balances. Now Mathematica automatically canceled the 2 from the 6 with a 2 from the 4 here and here. That's why it says 9 over 2 instead of 18 over 4, but that's fine. Now what we do know is that this fraction goes to 1, and this fraction also goes to 1, leaving us just with this coefficient of 9 halves. So our answer is 9 halves. Like that. And with that, we will be done for the day. So thank you for watching. And let me find my cursor. I hope that you're enjoying learning calculus. And I hope to see you again next week. Have a great day. Goodbye.